For a century, the automobile kept a highly stable physical form. It remained a four-wheeled metal box navigating asphalt roads. The computer did not. In 1945, the computer started as a rigid piece of custom military equipment. The ENIAC was built specifically to crunch the math for artillery firing tables. Operators programmed ENIAC through sheer physical dexterity. They hauled thick black cables and flipped thousands of switches to wire custom circuits for every math problem. So how did this physically bound calculator transform into a fluid tool that eventually swallowed our cameras, typewriters, and filing cabinets? The computer didn't magically evolve on its own. It achieved practical universality by constantly mutating to solve the specific bottlenecks of the communities that used it. To understand the machine, we have to look at how the world changed the computer. The first major bottleneck was time. Rewiring ENIAC took days of tedious labor just to set up a 30-second calculation. For ongoing military needs, this physical setup was entirely unscalable. This led to the stored program concept. Instructions were encoded and stored in memory, right alongside data itself. If held in memory, the hardware never has to be rewired. The machine simply fetches the next code and executes it. This birthed modern computer architecture. By the early 1950s, the business world had a totally different problem. Corporations required a way to process mountains of simple data, like payrolls and the census. Look at this IBM punch card. As you can see, the technology of the era was strictly limited by these rigid physical rows and columns. Processing records required armies of clerks physically carrying heavy stacks of these paper cards between specialized machines. EDVAC solved this by replacing punch cards with magnetic tape. A single machine could now automatically scan and process sequential records without constant human intervention. By shifting from a mathematical calculator to an automated data processor, the computer proved it belonged in the corporate office, expanding its identity in society. Meanwhile, aerospace engineers and nuclear physicists were working under the extreme pressures of the Cold War. They needed to simulate supersonic airflow and atomic chain reactions. These simulations forced a hardware crisis. The math required dealing with numbers that were either microscopic or astronomically large, which choked standard computers. Manufacturers responded by building floating-point arithmetic hardware. Floating-point arithmetic separates a number from its decimal placement, expressing it in scientific notation. Building physical circuits specifically to handle this automatically let machines calculate extreme values without slowing down. Processing speed was still limited by how fast the machine could access data. Engineers had to develop new memory technologies, like magnetic cores, just to keep these highly expensive processors fed. To eliminate expensive idle time, multi-million-dollar supercomputers used pipelining. Instruction pipelining is an architectural feature where the processor begins fetching and decoding new instructions while simultaneously executing old ones. The exotic, high-performance architecture powering today's everyday media streaming was originally forged by the absolute necessity of Cold War physics. As hardware got exponentially faster, a new, unexpected bottleneck emerged. The humans writing the complex machine code became the slowest, most expensive, and error-prone part of the system. Mathematician Grace Hopper solved this by introducing the compiler. It allows humans to write in readable logic, which the computer translates into machine code. This led to Fortran, the first widely successful high-level programming language. Scientists could finally focus on solving their actual problems instead of deciphering the machine's quirks. Isolated corporate users, frustrated by workflow inefficiencies, banded together to solve their own problems. Groups of programmers at competing aerospace firms wrote the very first operating systems simply to automate the tedious process of loading tape batches. Software finally abstracted the hardware away entirely, turning the computer from a physical machine you operate into a logical platform you interact with. Look closely at the modern smartphone or laptop you are currently using to watch this video. If we deconstruct this device, its core features, fast memory, operating systems, and pipelining, are the result of distinct historical demands. They are a living mosaic of the solutions developed for 1940s artillerymen, 1950s accountants, and Cold War physicists. The computer operates as a technological universal solvent because of its endless adaptability. It absorbs every other tool it encounters, because it was built from day one to reshape itself to our specific demands. Thanks for watching. Subscribe to the channel and join us in the next video as we explore the hidden histories shaping our modern world.